Now, coming up next, we have presentation on the preservation of the I-26 Green River Bridge in western North Carolina from John Sloan, the Bridge Program Manager with AECOM.
Thanks, everyone. Yes, my name is John Sloan with AECOM, and I lead the bridge team in North Carolina. I just want to thank Tim in particular and NCDOT for giving us the opportunity to work on this really neat project in the mountains of western North Carolina. It's located on I-26 south of Asheville. If you go south down to Hendersonville, you get to the Green River Gorge, where it's shown there on the map. The bridge, there are two original bridges that were built in 1968. They're about 1,050 feet long. The ridge line that you see in the background of the photo there is the Eastern Continental Divide. The Green River is on the east side of that, so it flows to the Atlantic Ocean. You've got 20,000 vehicles a day going across these bridges, very steep downhill grades coming towards the bridge in both directions, sharp horizontal curves. So it's a very tight spot, very challenging area. You've got mountains all around it. As well as the Green River Game Lands. It's a very sensitive environmental area. So very, very challenging location for a project. This is below the bridge, and as you drive across, you have no idea what's going on underneath. But these are massive girders. The web there is 14 feet deep. That's me shown in the photo. I'm 6.5 feet tall, so those are some massive bridge piers, massive girders. They were originally designed non-composite. This shows the typical section of the original bridges. You've got lightweight concrete deck that's only 6 3/4 inches thick. Stringer floor beam, 2 girder systems, so these are fracture critical girders, and 28 feet clear roadway there, going in each direction. I'll just point out the cross frames. You see the transverse stiffeners that are there in the photo, 23 feet 7 inches in between each cross frame. And here's the span arrangement. You have 2 approach spans that are 100 feet long. They're simply supported. And then a 3-span continuous unit, 260 feet, 330, and 260. And then it's 230 feet all the way down to the river. And the Green River there, you can see it a little bit. It's appropriately named. It's got a green hue to the river. There's just a photo of the river from the catwalks on the bridge, pretty far down. My understanding is that this bridge is the 3rd highest bridge on an interstate on the East Coast that carries interstate traffic. And this photo just shows, wanted to just point out the bottom flange is 30 inches wide at the pier, 3 3/4 inches thick. The web plates, again, I mentioned they're 14 feet deep and 5/8 inches thick. And then here's a photo of the pier. You notice the color of the pier. They're made out of concrete, but they have a stay-in-place steel form that was originally used actually for aesthetics, because the original designer knew that the weathering steel was going to bleed a little bit once it developed the patina onto the piers, so they used stay-in-place weathering steel forms just for aesthetic reasons. So I'm going to go through a brief history of the bridge, look at a feasibility study that we completed with NCDOT. We completed some load testing on the structure, and then final design. So for the history, the bridges were built in 1968. They added catwalks in 1976, 1984, guardrail was added. There were some issues and challenges that were discovered in the early 1990s that we're going to talk about. So there was a rehab completed then with some load testing, and expansion joints were replaced in 2012. So there's a photo of the guardrail that was added. Underneath of the structure, I'll just point out the K-frame diaphragms that are in the top of the photo. Then if you look on the left at the bottom flange of the girder, there are cover plates. These cover plates were added in the 1990s. And then the gusset plates where the framing members tie into the web. We're going to talk a lot about those because there were some issues at those gusset plates. Again, this is just a close-up view. You've got cover plates that are bolted on to the bottom flange there, and the gusset plate there that ties into the web. So in the early 1990s, NCDOT looked into this bridge and hired Lehigh University to do an assessment. Some cracks were discovered particularly in one location, span D, girder 1 at the bottom flange. They took several cores and discovered the crack that you see there in the photo in the upper right. So they did some hardness testing, chemical composition testing, and what they discovered was that one of the plates in the flange was not actually the correct steel, and so there were some original fabrication issues that caused the cracking. They were present since the fabrication. One other thing I'm going to point out on this slide is you see the three folks that are mentioned in that report. Sorry, I'm struggling to see their names here again. But Ben Yen and John Fisher, our technical lead on this project was Ed Zoe. He got his MS and his PhD at Lehigh University. He actually studied under Drs. Yen and Fisher, and Eric Kaufman was the lab manager while he was there. So Ed Zoe, who again was one of the technical leaders on this project, studied under these men who did perform this study back in the 1990s. This just shows a schematic of where the issues were discovered, again on the intersection of the bottom flange and the web. These defects were basically hydrogen-related cold cracking. They were present at the time of fabrication, so the bridge was carrying live load traffic for 20-something years before it was ever discovered. In this one area, the bottom flange plate was AISI 1045 plain carbon steel rather than ASTM A441 modified Core 10B steel that was actually noted in the specifications. There's, again, just a schematic of one of the cracks that was noted in the report. So what they decided to do to address this is they placed the cover plates, again, that you see there in the positive moment regions throughout the all spans, even though the crack was only discovered in one location. All spans, all the bottom flanges throughout the entire, both bridges, they put these cover plates in the positive moment region. In order to get across the splices, they had post-tensioning. This is just a schematic detail, again, from the plans in the early 1990s, where you've got a post-tensioning bar bolted on some pipes, and they post-tension across there. So I thought that was a pretty neat detail. Another challenge that they were facing back in the 90s was some issues at these gusset plates due to some vibrations with the framing members that were framing into the gusset plate. NCDOT has a record of over 500 pages of liquid penetrant mag particle and ultrasonic testing reports that were completed from July through December of 1992. What they ended up doing here was added that angle to stiffen the connection between the gusset plate and the stiffener. They also added this post here with the X-frame member that stiffened this X-frame, the wind bracing. This load testing diagram shows what was actually going on. As the live load would cross the bridge, the lateral braces vibrate for a significant period of time following the passage of a heavy vehicle. So you see the large hump due to the vehicle actually passing, but then you see all the small oscillations that occur due to the vibrations. So that was causing some issues and around where the gusset plates were welded into the web. They added some plates here at the K-frame. They routed out all the cracks in the gusset plates. A few additional details where they drilled out some intersecting welds, and I think the photo on the left is at a longitudinal stiffener. They had cut out some issues there. So they rehabilitated this structure. Again, back in the 1990s, we reviewed all of this data as we were going through our feasibility study. We considered several different options. One was mainly conventional rehab, creating a single bridge, which would be a really significant major rehabilitation. We looked at replacing the structure. This is a bridge preservation conference, right? So we didn't choose that one. But while we were doing the feasibility study, a hole opened up in the deck. This is a repair of that hole in June 2018. So again, you've got a deck that's over 50 years old. It did get overlaid in the early 90s, but even with that, weren't super excited about the state or the condition of the deck here. And also the fact that the structure was going to be still fracture critical. The fatigue on the bridge it did not have an infinite fatigue life. A lot of the fatigue details were developed in the 1980s. So if you go back to 1968, it wasn't really the fatigue-prone details at that gusset plate were a challenge as well. Looking at the 2017 inspection report, there were a few issues that were noted there, and NCDOT did some non-destructive evaluation. They hired S&ME to go out and evaluate some of the locations that were noted in the inspection report. S&ME did an outstanding job. I mean, they noted a few issues, some weld spatter, arc strikes, cluster porosity, weld overlap, and so on. A lot of it they were able to just grind out themselves. Some of the indications they were not able to remove, but all in all, there were only about 5 locations that were a concern, and so we addressed those in our rehabilitation plans. This is just a half section of our replacement alternative. I wanted to show this. Because if you do replace this bridge, you've got to raise the profile about 15 feet, massive amounts of earthwork. You've got to get down into the gorge to build piers. So you're, the immense amount of work there. The roadway length of the project is about twice as long as a rehabilitation project where you're going to tie the bridges together. So considering all these things, we consider the cost of the replacement at least 4 times the cost of the rehabilitation. And so NCDOT elected to go with the major, larger rehabilitation project where we would tie the bridges together. As we transitioned into final design, we did load testing on the bridges. We had 2 trucks that were provided by NCDOT. One was 72 kips, one was 67 kips. This helped us validate our modeling, our final design modeling. We had a lot of strain gauges on the structure. This shows at the pier on the bottom flange. We validated the fatigue stress range, so that one strain gauge is right there at the gusset plate. We validated that the cover plates on the bottom flange are participating in the system, so we had strain transducers on the top of the bottom flange and on the bottom of the gusset plate. They were recording essentially the same level of stress, so we validated those stresses and the behavior of the structure. We instrumented the floor beams, and we demonstrated that the transverse behavior is dominated by the floor beam. Those diagonals that you see there, have very little load in them under live load, so that was something that we were observing in our model as well. And then, so the previous was just a schematic. That's the actual instrumentation that we had on an X-frame. So I think we had, sorry, let me scroll down to my stresses here. We had 2.7 KSI as the maximum live load tension due to 2 trucks. That's in the bottom flange at midspan. And then at the pier, we had 1.3 KSI in the bottom flange. That's in compression. And back to fatigue, this was an idea that our load testing team came up with. We basically cut out a part of that gusset plate, so that increased our fatigue resistance, or allowable stress range rather. So we went from a category E detail to a category D detail, so that increased our stress range from 4.5 KSI up to 7 KSI. I'm going to go through final design briefly here. Mainly, first thing I want to just talk about is the team here. We had an amazing team assembled. Tim led the NCDOT team. Cameron Cochran with NCDOT Construction was instrumental as we talked through constructability. Many folks on our side as well. Could not have done it without all of these folks working together as a team. I wanted to show this slide because it's a multidiscipline project. We couldn't just rehabilitate the bridge. We had to go through work zone. We had to look at hydraulics, roadway design, the whole 9 yards. And hydroplaning was a big concern, and work zone were definitely a very big concern for us. This is the typical section that we ended up with. So again, we went from 2 separate fracture critical bridges to, we added floor beams in between the 2 bridges, new stringers, completely new deck, completely replacing the deck, adding shear studs on the top flange to make it fully composite, and then we strengthened the girders at the piers on the bottom flange as well. So when you combine all that, major rehabilitation and strengthening of the bridge. And I do want to show everybody the visualization that we did. All right, so we're still in construction right now. Let me show. So this is a photo from last summer. Floor beams have been installed. Again, the contractor's still under construction. He's working on pouring the deck right now. This photo was also taken last summer, and that's my presentation. I know I went through that fairly quickly. I tried to get us caught back up a little bit. I think we're a few minutes behind still, but I don't know if, I guess I'll turn it back over to you, Tim, to introduce the next group.
Okay. Thanks, John. I appreciate it. Yeah, thank you very much.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.